Hi guys, welcome to another Learn Electronics Repair video. As you can see, this video is kindly sponsored by PCBWay. I want to just catch up on the projects we have work in progress at the moment, and then I want to show you a really interesting device that I have that I bought in the 1980s, which you don't seem to be able to find anymore, and I was thinking we could probably modify this to make another interesting project and then get PCBWay, as they're sponsoring the channel for 12 months, to make us some PCBs. And I'm sure you'll find that really interesting. I'll just show you this. So these are the PCBs from the $1 short finder, upgraded. I had a few more. I gave half of them to Carlos because Carlos from Retro Upgrade also worked on the project with me. And if Detlef Amend, who designed the USB version, would like to get in touch with me, I'll send you a few as well, mate. Just let me know, give me an address, and I'll post some to you as well. So this project, and for that matter this one, are both on PCBWay's shared project. So you can actually order the PCBs from them, or you can actually order completely made units as well. I've got all the parts on order, so they should be here soon, so we can actually build some of these, and we can have a little play around with battery packs people were discussing. So this little device will fit on the back of your multimeter, and you'll have a 4-wire Kelvin probe. I'll just show you the project on PCBWay, and then we can have a look at the other things we can work with today. This is the project on PCBWay, and I will put the link into the description of this video. So if you want to purchase any of these, they'll be there for you. You can order now. But as I say, hopefully next week or so, we'll be able to build some of these up and give them a final test to see how the finished item looks. PCBWay also sent me, well, two actually. I gave one to Carlos at Retro Upgrade for his work on the project, but they sent me these little rulers, and I think they're really nice. I mean, these are like 99 cents. If you're ordering some PCBs, you can just tag one of these on your order, and I will again put the link in the description to this video. But I just would like to show you this ruler because I think it's a really nice little thing, a geek's toy. Yeah. So this is the PCBWay ruler. You can see it has holes through here, so it has different metric and AWG size wires, so you can poke your wires through, find out what size they are. It has some little schematics to remind you of the pinout of a MOSFET, and it has the various pitches, so you can effectively put a chip on here, and wherever it fits, that tells you the package type, QFP32, 0.5, 0.8 pitch, and so on. And on the other side, I like this. So these are all your different surface mount resistors and capacitors, and again it shows you the size both imperial and metric, which is very confusing I find, by the way, because like a metric 0603 is completely different from an imperial 0603, but they use the same numbers just to make life more complicated than it needs to be. Yeah, but again, you can place your components on here after you've desoldered it, and you can see what size it is, where it fits, and that's the package size. Yeah, for transistors and MOSFETs. I think it's just a really nice little toy. So, as well as all that, you can actually use it as a ruler. Yeah, different trace widths and so on. Anyway, as I mentioned, if you want one of those and you're ordering from PCBWay, they're 99 cents, and I think they're well worth having. Yeah. Anyway, let's have a look at the project we're going to work on this video. This is a American Audio VLP 1500 power amplifier, 750 watts RMS per channel, and this is actually a topic of another video which I'll publish when I actually manage to fix it. At the moment it's looking a bit complex. These don't normally fit in this way. I've just put them like this to work on. They're actually going sideways. But what I basically have is this channel is distorting even at low volumes, and this channel is good. And I've been trying to figure out what the difference is. I don't have any schematics for this. I can see it's distorting, and I can measure voltages and see there's something wrong, but I can't so far manage to pin down to what components. I've measured all the resistors and capacitors, I've used diode mode, all the semiconductors look good. So this just reminded me of something people were talking about recently. And this is regarding a piece of test equipment we used to have in the late 70s and early 80s. I certainly used them in the early 80s, and they weren't new then. And this bit of test equipment has kind of got itself something of almost a legendary status of late, and it's called a Huntron Tracker. And what the Huntron Tracker did, it had like an oscilloscope screen that displayed a plot, XY graph plot, like almost like a lithogist figure, if you know what one of those is. And it effectively injected into the circuit a low current AC signal. You could select the power, if you like, low, medium or high, and it measured, or rather displayed, the response of the circuit at that point to the AC. So for example, if there's a short, it would give a vertical line. If it was open, horizontal line. If it was resistance, it would give a diagonal line, and the angle of the line would vary with the resistance. If it was capacitance, it would produce like an ellipse, and again the angle of the ellipse would change with the value of the capacitance. And things like diodes, effectively, which conduct in one direction, would produce like an L-shaped display. So in the negative direction it would be horizontal, and in the positive direction it would give a vertical line. And you could look basically with this item, you had two probes, so you would connect it to the ground of your test device. You would take the two probes and put them on two identical circuits, one working and one not working, and it would show you by looking at different points if there's any difference in the response, and by doing that you could pin down where the fault was. So these Huntron trackers, as I say, become something almost legendary. You can find them, they're very expensive to buy, and they're very sought after, almost a collector's item. But I have something here which I bought in the 80s, which I modified to make it work like a Huntron tracker. I'll show you the device now, we'll try it, we'll have a look to see how it works, and then we'll look to see if we can change it to make a project, and PCBWay will sponsor that and make us some PCBs, and then we can build our own version, much cheaper than buying the tracker. So let me show you what I actually have. This is a HAMEG or HAMEG component tester. I'm English, HZ65. HZ if you must. Yeah. And this is a similar thing to the Huntron Tracker, but this is an add-on for an oscilloscope, whereas the Huntron Tracker was an all-in-one device with the oscilloscope screen built in. It has a little transistor tester socket here, so you can plug components in here and then connect your signal, if you like, between the various pins. And it also has two connections here for meter probes, so this is where you put your meter probes, your ground and your probe. And it has two connections here which connect to your oscilloscope, X and Y. So on the oscilloscope you put it into XY mode, connect this, and then it will produce a line on your scope basically. It's far easier to show you than to explain it. So let me get it set up and then I'll show you what this actually does. And there we have it set up. I've used some BNC to phono lead adapters because I don't have any BNC leads. So I've connected them to the X and Y input on the scope. So the red is Y. You can see here Y. X is voltage, which goes to the X input on the scope. There you can see X. So we basically get a horizontal line on the screen. Now, if I short the leads together, so the leads are connected to the other end of here, okay? Black and red, just normal meter leads. So if I short the leads together, we get a vertical line, okay? Horizontal line. And if I put a resistor in between them, we'll get a diagonal line and a capacitor. I'll show you. Let me get some components, you can see what this actually does. So This is a 47 ohm resistor. Let's connect it to our analyzer. And we get a diagonal line. And the slope of the line will depend on the value of the resistance. This is a 220 ohm resistor. We get a less of a slope, yeah. So the lower the resistance, the steeper the slope. This is a 10 microfarad tantalum capacitor. Let's just stick this across it. And you can see we get a kind of an ellipse, yeah. Let's just go the other way, see if it's any different. Should be the same, yeah, because it's AC. So that will give us an ellipse. This is a 100 microfarad capacitor. Gives us more of a circle, and a higher value capacitor will give us more of a vertical ellipse. There's a diode, or a Zener diode. That's a diode. So effectively you can see to the left, and if the horizontal part is where it's not conducting, and the vertical part is where it is conducting. And if I just set my display so I just alter the position, I've shorted the two leads together. Let me just alter the position a little bit on here so it's centered on the scale, yeah. Now you will see that the diode conducts just after the vertical point and then starts to conduct more effectively. It's like a slope, yeah. See it the other way? I'm just put it where you can see it. Go one way around. We can go the other way around, okay? This one's a Zener diode, a low voltage one, about 3 volts. So we should see the diode in one direction. Yeah. So just after the slope, sorry, just after the centre where it slopes straight downwards, that's in the forward direction. It's passing more current as the voltage increases. And the one that curves up, that's the Zener voltage. That's the reverse direction. That's the Zener breaking down, yeah? So Zener. This is a 5.6 volt Zener, so we can look at this one. Okay. Yeah. See the shape of that one? Let's compare it with the other one. That's the normal diode. This is the Zener. Yeah, see that one? And on this, effectively the horizontal part is longer because it's a higher voltage Zener. So that's what it does with Zener diodes, capacitors, resistors. This is a bipolar transistor. So we know a base emitter, base collector should look like a diode. Yeah, diode. Diode with a breakdown in the opposite direction. Collector emitter, we get a funny little waveform, yeah. And this is a MOSFET. Let's have a quick look at what we got. So between the gate, drain or source, horizontal. Yeah, that's giving like an L shape, like a diode junction. Okay, let me put the black on the gate. Now let's have a look. See, it's switched, it's changed, as you'd expect. So that's what this does. It draws little diagrams, if you like. And this is one of these things you kind of get used to using over a period of time. But what it can do very easily is show you when there's a difference between two circuits, if you have one known good one and one known bad one. Let's have a look at our amplifier using this and see if we can see any differences. Here is our amplifier. So we have bad channel and good channel. The way we'd normally use this is we connect the black lead to ground. So I'll find a ground point. The device is powered off, black is in ground, and now we can have a look around our circuit. So for instance, let's go like some of these resistors. I go to the end of this resistor here, and you can see that shape I get, yeah? And I can do the same on this one. And it's basically the same. And just go somewhere else, you can see a shape, and we can do the same on this one. Yeah, you can see there's a slight difference there. Yeah, I'm not sure how clear you'll see it, but there is. Just have a look on here, that's almost a vertical ellipse. Yeah, and this is what we can do with it. We can go onto the transistors. So base of this transistor is reading, well, you see it, yeah, base of this transistor is reading basically the same. Collector, you can see a little slope, and so on. Okay, so we can do that. And we can go around all our transistors and see if we can actually see any difference between the two. Yeah. But what the Huntron Tracker would do was a little bit cleverer than that. So with the Huntron Tracker, you do the same, but you have two red probes, and you can put them on both circuits together, and it'll switch between the two red probes maybe twice a second or something like that, once or twice a second. And you can see the display changes, it switches, and if you see a change switching between two patterns, you know you've got a difference there. And we can go on this IC, for instance. This is an IC there, yeah, and we can do the same on this IC. You can see it's basically the same, yeah, but it automatically switches between the two with two probes. So what I did with this little device is I made an add-on, a very simple thing, which I'm going to show you, and then we'll try it, and I'll show you this is effectively how a Huntron Tracker worked. And now let's see if we can improve the design sufficiently to be able to actually reverse engineer the Schematic tester and my add-on. So this was my home built add-on. Basically you have two wires with plugs on, so these connect to the component tester. We can now connect the ground lead and two red leads. Inside here basically is a little oscillator. I can't remember if it's an NE555 timer or some transistor thing, but it was a long time ago when I built this. And the relay just switches between the two red probes. This goes clunk, 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 switching the relay, and now we can put our two red probes on together and we can see any difference straight away. So first of all, let's plug this in and let's see if this actually still works after, I don't know, 30 years maybe since I last tried this. It's still got an English plug on the end of it. Yeah, before we even had moulded on plugs, put Spanish adapter on. So let's see if my little device still works or whether it just wants to go bang. Yeah, ready? Oh, it's working, yeah? I forgot about the little blue light. Maybe it wasn't quite so long ago with blue LEDs. When did they come out? Anyway, that's doing its stuff, yeah? So we'll connect this to the Schematic and we'll connect some meter probes to this. Well, it makes a rather fun noise, doesn't it? So I now have the two red probes, okay? And I can show you if we just connect one red probe and we look at this oscilloscope. Yeah? As it's switching. If we connect both of them to the same place, we get the same waveform, a little flick going there. But we have the same waveforms. If I go to the same place on both amplifiers, I get the same waveform, yeah? So with this now, I can actually probe around the amplifier and see any differences between the two channels. And this is quite useful. Let's have a little bit of a nosy around our amplifier. Yep, same place. So you see it's the same, yeah. Ah! No, it's the same, I just didn't have a good connection. But that's what would happen if you had a difference between the two. Yeah, you see they're basically the same. And that's the problem I have with this amplifier at the moment, by the way. I can't find with my test meter a difference between the channel which is working and the one which is distorting or not. Any great difference with resistances. I can see voltage differences, so I know it's not the same, but I can't find the components. And I was hoping maybe this would actually... Yeah, okay, I've actually found a difference there, yeah? Something different between this point and this point on this transistor. On this one. Yeah? See that? You can see that there. That's got a resistance. No, they're the same. I just didn't have a good connection again. It was a bit of a red herring, but you can see how it effectively would work. Yeah, I get a good connection onto it. No, they're the same. Yeah, so you can see how this is working. I hope you can see it's a really useful bit of kit. and we can probably build one very cheaply. So let's take these apart and let's have a look to see what's inside them. This is the simplest part of it then. So as I explained, this is an oscillator, probably running at about 2 Hertz or something like that. Nice beat for a disco track, yeah. 120 beats per second or something. And you can see, yeah, there's a 555 timer, a little mains transformer. Obviously this is pretty much all salvaged bits, and a relay. So that's how that's working. It's quite literally connecting the red probe coming in to the sockets alternately. The black one just goes straight through. In fact, you can see it's wired directly there. So that's how that part of it works. You can see this is not a very high-tech device, and I probably didn't put a lot of thought into how to do it. I just used this relay. Apart from making a rather fun noise while it's working, I don't think there's any actual disadvantage to doing this. I don't see it's really, although it's such a basic way of doing it, wrong or bad, if you know what I mean. But I'm also pretty sure we could replace the relay with some sort of multiplexer IC or something. We need something that basically just passes a low voltage, low current AC signal when it's activated and doesn't pass it when it isn't activated. A low voltage sensitive triac maybe, or as I say, some sort of 4000 series analog switching IC or something. I'll leave that to you guys, yeah. Get into the comments below and let me know, A, is there anything wrong with that? Because it does the job as far as I can see. And B, is there a better way of doing it? The only thing I can see you're going to gain is the not having the clunk noise. I also accept this because it's switching the relay, that at some point it's off between the, effectively the two connections. It puts a slight horizontal flicking line in the display, but I don't think that detracts from the use of it at all. Let's have a look at this HAMEG HZ65, yeah, HZ65, go on, HZ. I don't believe these are available anymore. I had a look to see, can I buy these, and I think the answer is no. If there's some sort of equivalent of it, I don't know what it is, but I don't think this is a very complicated device. So let's have a look inside it and let's see what's in here. Well, this device doesn't seem to consist of anything very much at all. And we have 2 3-position switches. We can get switches easy enough. We probably don't need one of them because one of them is for using the inbuilt component tester, which we probably don't even want that. So we probably only need the one, a green LED, a few resistors. And that's about it. I mean, this is for the component tester, we probably don't need it. There's a transformer in here, and I need to just figure out how to open this up to have a look. There's a potentiometer for adjusting something there. Looks like if I undo these 4 screws, I can probably get this apart. So I think the only complex thing about this might be the transformer. I mean, it appears to have, just looking at it, a primary here. That's just the fuse holder. So it looks like it just has a primary and a couple of secondaries. I can't easily get it apart, and there don't seem to be any markings on this. I might find the schematic for this actually if I look online. So let's just pop this back on here, and let's have just a quick look around with the meter probe, so just see if I at least figure out how many windings there are on this. But it does just seem to be effectively an AC voltage supply. It makes me wonder if you even need to do this, whether you could do something using low frequency sine generator maybe. Another thing makes me just think about these testers, because they are very good, is why they don't seem to be around anymore. Is there some problem using them with modern low voltage electronics? That I don't know. I mean, we used to use them back in the 80s on computer logic boards, so they were fine at the time. But there may be some reason why they're not around. But having said that, guys, I mean, there's lots of old stuff to fix, yeah. And certainly for amplifiers and that, especially where you have the two identical channels, I think it's a rather interesting bit of kit. Let's pop this back on here. Okay, 2 screws will do for now. Let's have a quick look to see how this is connected up. Let's just go into continuity. So what do we have? We have power coming in. That's got a resistance. This is the other power coming in. I'm assuming one end goes via the fuse. Interestingly, it doesn't seem to. That's strange. No, the fuse must go from here to here. Yeah, it does go to the fuse. The fuse reads 100 ohms. Is that a normal fuse? Oh, the fuse reads 100 ohms. It's fun, isn't it, for a fuse? It has a rather strange fuse that reads 103 ohms. Meter's working. Okay, that's an interesting fuse. And then the other side of the fuse goes to one end of the coil here, and I'm guessing this is the winding primary. Let's go on to ohms raised, because it seems to be a higher resistance than the continuity wants to be. Let's look at this fuse again. Fuse is definitely 100 ohms. About 1k. That's connected directly to there. About 1k, and that comes back to here. Yeah, so we have about 2k. Quite a high resistance winding. And what's on here? Do we have two? No, I think we have one secondary winding. Yeah. In fact, I can see that that point there is connected directly to here anyway. So I'd say we have what we just have one secondary. That's strange. It's a bit of an odd thing, this. Yeah, it looks like it must be 2 secondaries in series. Can you see it? You can probably see the trap coming through here. Let me get the torch, you'll see it a bit better. You can see the 2 middle pins effectively connecting to each other. Let's try the torch the other way. And the switch is connecting to here. But this will be a low voltage AC supply. I mean, we can plug it in and have a quick look with the meter just to see what's on here. And that we've plugged in, we switched on. Let's go to, well, we want AC volts. AC volts. Okay, let's have a look what we've got. So, from here, there's about 8 volts AC, so that is effectively, those two are not connected together. Yeah, this is the same as there. We have about 8 volts AC. 8.1, 8.7, so what's across this one? Well, that's got 8.6, and that's got 8. And yet there's only 8.6 across the two. This is fun, isn't it? Let's see if we can actually find a schematic for it. Yeah, I think I have what I need here. It's not very clear. I'm sure I can find a clearer one. But this is the schematic. So we have just a transformer which is switchable 110 or 220 volts, but we don't need to worry too much about that. A transformer will do. We have 2 secondaries in series, 4.1 volts each, giving 8.2. I would have thought we could use a 6 volt or a 9 volt transformer, just a standard one. We have a rectifier, diode and the LED, and we have a few resistors. And that's basically it. I mean, this component tester thing we don't really need, so we would only actually need just the switch. And it looks to me, effectively, you're connecting either a 22 ohm, a 220 ohm, or a 2.2k resistor to ground. That's one of your test leads. And the other test lead goes via a 1 meg ohm variable resistor and a little capacitor to the other end of the transformer. Yeah, so in from the transformer through the variable resistor on the X output, and then the Y output switches between 3 resistors and comes back to the ground. And this thing we can just ignore. There's a resistor in there as well, but now I have this, that's 180 ohm I think, but now I have this barely readable schematic and I have the device. It's going to be so simple to make something like this. I don't see why we can't just use any transformer. Quite why the fuse is 110 ohms. I'm just going to have a look. This is the fuse T, which I think is slow blow or time delay. So 32 milliamp fuse. It's just a very low value fuse. It really does read 110 ohms, which I found a bit surprising, but I'm sure I can find, I probably have in my stash of stuff some fuses that are similar in rating to that one. Yeah, I had a quick look. The smallest I have is 125 milliamps, but I'm sure if I wanted a fuse of this value I could probably find something somewhere. I'm guessing that's why it has a high resistance. There's a lot of winding on there basically. Let's have a look at how this actually works then. I'm going to simplify the schematic we just saw by taking out the switch that switches to the little 3-pin socket for pushing transistors and such like it, because we don't need that, and also removing the power on LED and resistor because we don't really need them either. And let's get down to the basics. So what we have here is we have a transformer secondary. It's actually 2 in series, but that really isn't relevant, so we'll just draw one winding, and this is 8.2 volts AC. Okay. And basically this end of it goes to the red banana socket. This is your red probe for your device under test. So this is the device under test that we're probing. The black socket then comes back along here and it goes to a switch, which is a 3-way switch, and we'll just put our switch in here. That should do. So from our switch we then have 3 resistors, which can be selected with a switch, of course. So we'll put the resistors in. There's our 3 resistors. And the 3 resistors come back to here. The resistors are in fact a 22 ohm, a 220 ohm, and a 2.2k. That's the resistors. These select the current, so effectively we have high, medium and low. High is 350 milliamps, medium is 35 milliamps, and low is 3.5 milliamps. So that's our switchable current ranges. So that's how that works. Now we need to monitor the voltage and the current on the oscilloscope. The voltage is quite easy actually. So the voltage we have from here, a capacitor, 0.1 microfarads. That comes down to one of our oscilloscope probes basically. And from here we have a variable resistor, which is a 1 meg It's actually a little trimmer pot, so it's just set to a certain value, and the trimmer goes directly across the AC. So the setting on that will set the voltage here, and that basically just depends on the AC waveform. So this just gives you a proportion of this. If it was set to the middle, it's 4.1. You know, we can vary it between basically 8.2 and 0. That is our X. Yeah, that is the X input on the scope. Okay. To have a scope, I'll just draw a little BNC type thing there. That's that one. Okay. Now the other thing we need to monitor is the current, and we monitor the current here. So basically, this is the voltage drop across the resistor is proportional to the current, and this goes to the other oscilloscope probe, which is the Y input. Okay, so I say oscilloscope probes, they're the BNC connectors, so that goes there. Ground is an actual fact. This is our black test lead. Ground is here. Okay, and that connects to the outer screen of the BNC connectors. Okay, like so. And that is basically it. That's all there is in the device to make it work. So it occurred to me I can probably actually build something like this into my little switcher unit that I made. I'll just show you what I have in mind. This is a little switcher that I built, which I've just shown you, so I can probe two circuit boards at the same time, looking for differences. And I'll just show you how this connects to the component tester. On the add-on then, I basically take the wire to the red lead, and this connects to the actual relay. So this goes to the relay contact, and that switches between two probes. So these are my two red probes. And the relay, I'll just draw the coil here. Is switched via a transistor. This is to ground. I'll draw like a chassis ground to make it different from that ground because it's not the same point. And that goes to my 555 timer. Okay. This then goes to a large electrolytic capacitor like so, which is connected to a bridge rectifier. We'll just draw it like this. Negative going down to here, which is basically the same point as here and the same point as here, yeah. And then the AC inputs on the bridge rectifier are connected to the primary. I should have drawn it the other way around, it would have been easier. Oh well. Voila. Okay, so that's how it effectively connects up. And then of course we have the primary. This, I think I said primary, secondary, yeah. We have the primary here and we have 220 volts AC. So that's effectively what we have. The little 555 timer circuit, I didn't design this, it's something I found off the internet. It was a long time ago, but I've just found something which I think is very similar, so I'll just show that to you now. You can see the transformer is actually a centre tapped 0.6 volt, 0.6 volt, giving 12 volts. It probably isn't very accurate, it's probably more than 12 volts in actual fact. And the 12 volts effectively, that's the bridge rectifier, which I mentioned here. This is the large capacitor, which is here. This is the timer IC, which is here. This is the transistor, which is this one. And this is the relay. There's also a diode across the relay, just to stop any back EMF, which goes like so. This is to stop the transistor being damaged by the back EMF when the relay switch is off. I did the whole tutorial on inductors. If you want to understand that, I'll link it from this one. So that's basically what we have here, is basically this. Yeah, you can see it. So what I'm thinking we can do is, we can connect directly from the AC here, 0.6 volts, which is a bit less than the 8.2, but I don't think it's going to be critical. And we can tag this circuit here, which is very simple. One switch, 3 resistors, a variable resistor and a capacitor. We can tag this on to the secondary of the transformer. One side, effectively one half of the center tap, 6 volts. We can fit here, I think, some phono sockets, because I don't really have any proper BNC leads anyway. I do have BNC sockets, but we can put a couple of phono sockets and connect this to our oscilloscope using some phono to BNC adapters, which is what I was doing before. Effectively these things, phono lead in, BNC. So let's build that, and let's try to make it to fit onto the top of this. I can put the switch in the middle, and then there's enough of a gap there for the switch to go, and then all the other parts can probably be stuck straight to the top of here with a little bit of vero board again. We can put that together with the resistors on top of here. We can put the phono sockets on top of here as well. In fact, the whole thing probably doesn't even need any vero board. It can be tagged together, I would think. Let's have a go. And then let's try and build that and see whether we can integrate the whole thing into here. Okay, I have all the bits I need. The 3 resistors, the 1 meg trimmer pot, the salvaged 100 nanofarad 0.1 microfarad capacitor, a little rotary switch, 1, 2, 4 position. Well, I can use it for 3 position. It's just a salvaged thing. With some phono sockets. I can cut the yellow one off. You see they're not exactly wired to each other. I can just take that off, and I've just got the red and white. And I'll mount the switch up on the lid, as I mentioned, and then I'll see if I can just wire it up on the back of here, to be quite honest, especially if I can mount the sockets on here as well. I'm pretty sure we can do that. Then the red and black coming in here, which were coming from the component tester, they effectively go to the AC directly on the transformer. So you can see here, if we look at the diagram again, from the transformer, red just goes straight to it, and the black one goes via the switch. I fitted the switch on here. I fitted the 2 phono sockets a little bit crooked, but this is a prototype. Although I must admit I would rather go a little bit straighter than that. But there you go. So that's done. I've taken the circuit board out. I can see how I built this now. So these are the 2 secondaries, 0.6, 0.6. And I'm not using the 12 volt. I'm actually using 6 volt. So this secondary is going here and here into the bridge rectifier, and then the plus and minus are coming out there. So that's the bridge rectifier, that's the capacitor, which means this secondary isn't being used at all. It's isolated from that one as well. So I'm going to use this secondary to power my component tester. So what I'm going to do is, I've got some of these little headers, pin headers, is take the middle pin out. Yeah, so I've just got the 2, and we'll do the same with the other one as well. Okay, and then I can solder them in, obviously, from the other side, so that they connect into these secondaries. I'll put them somewhere down here, and then effectively I'll have the AC either side. I'll have 2 of them, so I can use one to connect to the circuit that's going on the back of the top panel, and then one to connect to anything else that's on the bottom, basically. So I'll solder those in there, and then we can maybe start putting this together a little bit more. So I've soldered the pin headers here. So this is the 6 volts AC off one of the 2 secondaries, this one I think. So the red wire now no longer goes to the connection here, it just goes to the relay. So that's this wire coming up here. These are now connecting to the relay, they already were, these are the 2 red sockets. So this goes to whichever side we want to call the red side, and then the other side goes to the switch. Yeah, and this also goes to the Y output. So we'll put this red wire on first. I've soldered that on there because this just goes to the relay switch. Yeah, with 10 switches between these two. So that's going there. The other connections actually go to the circuitry, which is all on here. So basically the red input also goes to this capacitor and variable resistor, and the black input, if you like, from the AC goes again to the variable resistor. It goes to the resistors which are going to be on the back of here, so the variable resistor will also be on here, and the 2 sockets which connect to the oscilloscope are also here. So what I'm going to do is with this, I'm going to use just it's off an old PC fan, and that can go on there. So that's the 2 connections running up to the top. So we can cut the red one off. It's not used, but we might use it for a bit of wiring, I suspect, on the front panel. And now we can put everything together on the front panel and just connect it to the unit. So let's start putting all this together. Okay, so I've kind of marked on here black and red so we know what we're talking about. That's effectively the wires coming up here, but it's actually black and white, but we imagine that's red. Yeah, I've marked the switch, I've just checked it out. It's actually a 3-pole 4-way switch. So if we put it fully in the anti-clockwise direction, this is one of the poles. We only need 1 pole, that's connected to there but not elsewhere. We just move it over 1, that is position 2, it's no longer there. Yeah, and move it over again, that's position 3, and the other position 4 can be off. So let's have a look. That is effectively low, medium, high. We'll just do it that way, high, medium, low. So low current is the highest resistance, which is 2.2k, 220 ohm, 22 ohm, and we can use that as an off position. I don't see why not. Okay, they're all soldered. The 22 ohm is actually a 2-watt resistor. I happen to have some. The other one's a half watt, I believe. But the one with the lowest resistance is when the most current flows, so that's why I put a slightly larger resistor there. I didn't actually bother to do the ohms law to see if it's enough. We'll find out, won't we? I should do, really. Let's have a think. So we'll call it 6 volts AC, and we have to work out the current that's flowing through 22 ohms and then multiply it by the voltage. Let's just do it anyway. I think it's going to be okay. So 6 divided by... In fact, no, I'll tell you what, let's call it 9 volts. I mean, it isn't that much. 9 divided by 22 equals... Find equals a 0.4 of an amp times 9. Oh, 3.68. Well, that's for DC. I mean, considering this is like AC, so there's some sort of root mean square, and it probably isn't 9 volts. I think 2 watts is just about enough. We'll find out. So we can now just effectively join all our resistors together here, and this can go on to the white one, and that can be our Y input. Very Heath Robinson, this, isn't it? It's a prototype. Yeah, I'm sure we can build something nice with PCBWay's help once we've tested to see if this actually works or not. And of course it moved. Let me just push it down a little bit. I've got it. I got it and it got warm. Okay, so that's on there. So that's the connection to the Y input. Anything else that needs to go on here? Yeah, the black wire. So that can come from our little plug that goes to the other side of the unit. Doesn't need to be too long, but we'll leave ourselves, you know, a bit of spare room. Yeah. So our black wire we can also tag on here, and it looks like we can pretty much use this as a mounting point for just about everything else. Actually, put a black wire on here. Okay, there's the black wire attached on there. That. The potentiometer, I think we can mount off here. So this goes to one end of the potentiometer. So let's find that. Okay, so this is the potentiometer. I think we can just mount this on here. Actually, sideways, we can get to adjust it. So let's put that there. Let's just hope nothing's going to actually hit anything when we put this back together. We can have a quick look. It goes together at the moment, but these switches are quite close to this relay. So I'm going to mount this, in fact having nothing further over that way than that. You can see if I put the two together, it's quite close to the relay, but we've got a lot of space over here. So let's have a plan B and mount our potentiometer, I think, on here. Well guys, by more luck than judgment, this worked out quite well. So we have the capacitor from the wiper of the variable resistor to one end of it. So you can see here, one end of the capacitor goes to the wiper and the other end goes to here. Yeah. Now this end effectively goes to the red wire. So I've tagged it on there. That's the red, white wire in our case. So the white wire is here, the junction of the end of the potentiometer and the capacitor. That's the red wire. This pin, which is the wiper and the other end of the capacitor, goes to our X input, which is the red input on here. So the wiper actually goes to there, yeah, and the other end, which we haven't used, goes to the black wire, and the black wire is here. So if I've now mounted that across there, that's our white come red wire. I can now mount the variable resistor across here, and we have the correct connection. Look, eh? So what we have left to do now is the ground of the X and Y, that's these here, both connect together, and they go to the black probe, which is also the center point of the switch. So if I connect the two grounds there to the center point of this switch, I can then take a wire from here to the black probe. Yeah, so I've already got those on here. So that's where we connect to the black probe as the center point of that switch. I've put probe rather than black. This is the black wire in here just to save some confusion. And these red I've mentioned here are probe. We'll better call our red wire a white wire, haven't we, just so we don't really get any more confused than we might be. Okay, so I'll put the two connections from here to the switch, and then we can connect the wire coming here, which goes to the black probe, to the switch. And there we have it all put together. So I'll just double check to make sure I didn't forget something. Obviously this needs to plug onto here. I should have put a connector on here, but I just didn't have one to hand. But it's easy enough to open up and work on if we need to. It'll certainly, let's just make sure it fits together at least. Let's get in line with the LED. Yeah, it goes together as well as it did. It didn't quite fit together properly before because the transformer's a little bit too thick for this case, yeah, but for a prototype it's kind of in one piece, yeah. So I'll just double check the work, and if I'm happy with that, let's try it. Okay, that looks good. We need to set the potentiometer. I'm not sure what we need to set it to, especially because our voltage is probably not the same as the voltage on the original one. But what we can do is a good start, I guess. And by the way, their 22 ohm resistor is bigger than mine. We should be using a 4 watt. So that's something we need to change on the final version. But we can test, I'm sure. if we have a look at the potentiometer on here, which is here, and just see how it is set. Now if we set ours basically the same, I don't think we'll go very far wrong. I suspect that alters the scale, so we effectively get the vertical and horizontal lines the same size on the scope. So we are ready to try this. Let's see, let's connect it up and let's see if it works. I have it connected to my oscilloscope. Let's see what it does. So we'll just connect one of the reds to the black. And you can see it's basically switching as you'd expect it. But it does slow down a little bit. If we connect the other one, it actually speeds up a little bit. It seems to me that what's happening is that the fact the relay is drawing current from the transformer is altering the voltage slightly. So why I think this is actually kind of like moving in and out a little bit. Just try a diode. Yeah, let's see if we just zero it so it's kind of centered. Let's see if that stays the same as well. So I've now got the vertical line centered. Let's try the other one. Yeah, it stays centered. So let's just try a diode. So red to the cathode, why not? Yeah. Other way. So it's working. Let's try the other red. But it speeds up a little bit. Yeah, you can see that, can't you? Slows down a little bit. Let's now effectively use them both to measure the same thing. Yes, the pattern stays the same. It speeds up a little bit. So I'd have to say, guys, this works. Yeah, this works without a doubt. The only issue is that I can see is that the relay is drawing a variable amount of current from the transformer and therefore affecting the display slightly. So it probably wants a little bit of tweaking. What I have just done, previously it was set to the high current position, so this is drawing about 350 milliamps. I've now set it into the low current position, and you can see it doesn't speed up or slow down. Let's go to the middle position. So this is the 35 milliamp. Yeah, and it doesn't affect it. So it's only in the high current position. I mean, maybe a larger transformer would solve that. I'm not sure why it speeds or slows down. I'm guessing it's a combination between the current on the high range and the current the relay is drawing as well. Still, yeah, something worth talking about. Let's have a quick look at it on the amplifier again. Here's the amplifier once again. Here's the two red probes on the home built tracker. I have the black lead in the ground, and let's just try it. And you can see there's no difference there. No difference there. No difference there. Let's try another one. Let's try with these transistors. So we don't have a difference. It's a bad connection. Yeah. So look at around the ones where I know there's a problem with this. See if we can see any difference. No, it's the same. So that's working just as well as the original, to be quite honest. And there you have it, guys, how to build a Huntron Tracker clone without breaking the bank. Most of this was salvaged parts. I think the only thing that would actually cost any money is the transformer, the relay, the switch a euro or something. It really didn't cost much money to put this together. I suspect within the enclosure and everything else, you can probably build the whole thing for like 20 euros. Interested to know what you guys think in the comments below, yeah. But if you've not seen one before, very handy little device, certainly a lot of fun to use, and I hope you enjoyed building that with me, yeah. I'd like to thank PCBWay once again for sponsoring this video. I will now have a chat with Carlos at Retro Upgrade, as I did with the previous project. We'll get the PCBs designed, the bill of materials all made up, and get the PCBs built by PCBWay.com, of course. They will send us some free of charge sponsored samples, and we can see how well it works. The only thing it probably didn't do is in the high current range, the 350 milliamps, it does work, but it affects the switching speed a little bit. And the issue of whether there's a better way to do it other than using the relay. Is there some device we could use, 2 of them, we could switch alternately, which is completely solid state, that can handle 350 milliamps, but also supply low currents, 3.5 milliamps, without distorting the waveform. We need effectively the AC to come through as is when it's switched on. Some of you guys, I'm sure, have some thoughts on that, so once again, in the comments below. But for now, I'm very happy to use this. You'll be seeing this on future videos, no doubt, and you'll be seeing the final version with the PCBs very soon. Okay, hope you enjoyed that one. I'll see you all soon on another Weird Electronics Repair video. Ciao for now, guys.